Hello and welcome to the inaugural video of the Mathematics YouTube channel. Thanks for joining me, I guess. This is hopefully going to be a one-stop shop for a smug, nasally voice over explaining HSC maths concepts with some very basic video editing and some very stale memes. So it should be heaps of fun. Today we're going to be looking at some HSC problems involving maximum minimums in the applications of calculus topic. We're going to be looking at three problems. One of them is easier, the other two are quite challenging. Apologies, these questions are pretty time consuming, so this might be a bit of a long one for the first video. So, alright, let's kick off. Okay, kicking off with the first one, we have a wide enclosure. We have a farmer wishing to make a rectangular enclosure of 720 square meters. That's right, women can be farmers, you guys need to get woke. She uses an existing straight boundary as one of the sides, that's the shaded grey part. And she uses wire fencing for the remaining three sides, which divide the enclosure into four rectangular areas of width x meters. Okay. Show that the total length of wire is given by L equals 5x plus 720 divided by x. That's for 1 mark. And then for 3 marks, find the minimum length of wire required, showing why this is a minimum length. Okay, this is from the 2016 HSC exam. It's a band 4 question, so if you're hoping to get a mark in the 70s or above, you'd want to be getting these questions right. So feel free to pause the video and have a go by yourself first. That'll likely make what I'm about to say make more sense, and it's just good fun. Or if you can't be bothered or you're not sure where to start, you can just sit back and let me do the talking. If I'm going too fast at any point, feel free to just put the video on half speed, I guess. Alright, kicking off. We have the total length of wire. So to build this enclosure, we have these 5 lengths here and this one width down here. Okay, so it should be obvious that all these lengths here are equal to x, okay, because they're all the same rectangle. And now we just need this measurement down below, which I'm going to call y. Okay, the key part of the question is that the area of the entire closure is 720 square meters, which means that theoretically, if we did x multiplied by y, we would get 720. Okay, that's good because we can rearrange that for y, and now we have an expression for the length of y in terms of x, okay, because our question is all in terms of x. So now the length of y should be the 5x's plus together, plusing with the y, and given that y is 720 on x, we get the target as required, and now we just say QED, which is Latin for quite easily done. It's just a really nice way of sort of smugly mocking your marker and saying that you're smarter than them. Yeah, just a bit of a power move, really. I always look forward to it. Okay, now that we've done that, we can use that equation to answer the second part. Okay, and usually these questions are designed so that they give you the equation for part I, and then if you can't find it, you should still be able to do the second part, which is the calculus. Okay, so keep that in mind. If you can't do part A, don't give up, just do part B instead. Okay, find the minimum length of y required, showing why this is a minimum length. Okay, so if you think about this function here, this is a value of x giving a length. Okay, I took the liberty of putting this function into a graphics calculator. Shout out to Desmos, today's sponsor. I appreciate your support. Okay, it looks like this. So we have a function with two turning points, right here and right here. This one I really could care less about because it's a negative value for x, and in this question a negative length really doesn't make sense. So I'm just going to be focusing on this one here. Okay, it's a minimum turning point, which is good because we're trying to find a minimum length. So our goal is really just to find this minimum turning point for this function. Okay, and we've done that heaps of times. The way we approach that is we find the derivative and we solve the first derivative equal to 0. That's what we're going to do here. Okay, we're just going to find this minimum turning point and we're going to show that it's a minimum turning point. So first things first, I'm going to write this in index form, 720 x to the negative 1. Now I'm going to take the first derivative, dl on dx. So 5x derives to 5, and the 720 gets multiplied by the minus 1, and now take 1 off the power. Okay, if you prefer, you can write that as 720 over x squared, whatever works for you. And now, like I said, we're trying to solve where that is equal to 0, because that's where your stationary points will be. Okay, so we're solving first derivative equal to 0. We can add the 720 divided by x squared across. We can multiply the x squared across to the left. Okay, multiplying across. And then we can divide both sides by 5, get 144. and then we can solve for x by just taking the square root. Normally in this case we would expect a positive and negative answer, but as I mentioned, we don't really care about the negative one because this is a length, it has to be positive. Okay, so you may feel like you have completed the question there because you've done a lot of work and you got an answer, so you may be like, all right, sweet, let's keep going. Unfortunately, in a 3-mark question, that's really only at max 2 marks, okay, because the question asks you to show why x equals 12 gives a minimum length. Okay, the way you need to show that is by using the second derivative. Okay, if you can show that the second derivative is positive, that means the curve is concave up, which means it must be a minimum turning point. Okay, so usually with these questions we need to apply the second derivative to show that it's either minimum or maximum. Okay, so we'll take the second derivative, so we'll just take our first derivative, going to write it back in the nice form of x to the minus 2. We're going to derive that again. Okay, so 5 derives to 0, the minus 2 comes down and multiplies to make 1440, and now we have x to the power of 1 minus from minus 2 is minus 3. Okay, and again you can write that with positive indices if you prefer. Okay, so now what we're going to do is we're going to sub x equals 12 into this second derivative and see what happens. Okay, so at x equals 12 we get 1440 over 12 cubed. I don't actually care what that number is. What I care about is that is a positive number. It's greater than 0. Okay, because greater than 0 means you've got a smiley face. It means you are concave up. Okay, so if we have a stationary value and the curve is concave up, it must look like this. Okay, it must be a minimum turning point, which means that we have a minimum length. Okay, so that's all you need to show to your marker to get that, that extra mark. You need to use a second derivative to prove concavity and make a conclusion. Okay, and now the last little part of this question is that we weren't actually asked to find x, which gives the minimum. We were asked to find the length of y, which is the entire boundary. So we go back to our original function, L equals 5x plus 720 divided by x. We sub in our value of x equals 12 to find the length of y, which is the smallest possible. Okay, so subbing in 12, we get an answer of 120 meters. Okay, now that is our final answer. That's our full marks, full 3 marks. It's quite a bit of work, but the questions always seem to follow this kind of formula of form a function, derive it, and show that it's a minimum maximum. Okay. Okay, now we have the next one. We have a cone inside a sphere. The sphere is radius A, center at O. The height of the cone is x, so this cone is x tall, and the radius of the base circle for the cone is r. Okay, show that the volume of a cone, of this cone, sorry, is given by 1/3 of pi times 2ax squared minus x cubed. That's for 2 marks, so it will be a bit of work. And part B, find the value of x which maximizes the cone, and again we need to give reasons. Okay, this is a 2006 HSC question. It's a band 5-6. This is an upper level. So marking the 80s and 90s, so it's going to be pretty challenging. All right, once again, pause the video, have a go if you so choose. Okay, so we're going to do the first part, which is showing that the volume of the cone is given by this expression. So first of all, first thing we need to know is that the volume of any cone is 1/3 of the base area, which is pi r squared, multiplied by the height. Okay, so that's kind of assumed knowledge for this question, unfortunately. If you don't know that, you are shit out of luck. Okay, so now we notice that the height of the cone is x. Okay, so that's good. That h is now going to be an x. So we have the 1/3 pi already good to go. What we need to show is we can turn r squared into something involving 2a's and x's. Okay, so in order to do that, there's a few things you need to notice from this picture that make this question doable. First thing you need to spot is that from O to the top of the cone, given that O is the center of the circle, this distance here is the radius of the sphere, which is A. Okay. The second thing that's useful is that, well, if this height here is x, and we just said this value here is A, this distance here must be x take away A. Okay. Now that's all you need to apply the algebra to find the expression for r squared. Now, seeing as we have a right angled triangle here and we're trying to find r squared, Pythagoras is going to be a good instinct here. So we'll write our Pythagorean equation for this right angled triangle. So we have r squared plus x minus a squared equals a squared. We're trying to find r squared, so we'll take that x minus a squared across to the other side. Now we'll expand the brackets. Keep in mind this is a perfect square, so be careful. should get x squared minus 2ax plus a squared. We'll expand out the negative, and now we'll just simplify what we can. Luckily, the a squareds cancel each other off, and we end up with 2ax minus x squared. Okay, so now we'll take that r squared, we'll put it into our volume formula here, and cross our fingers and see what happens. So we get this, which is almost there. We just need to put this value of x multiplied inside the brackets, and we get 2ax squared minus x cubed. We've done it, QED, in your face, we're the smartest. Okay, so there we go, that's part 1 done. Now we can do some calculus in part 2. This is where the fun begins. Okay, so we're going to find the value of x which maximizes the cone giving reasons based on the function we just found. Okay, so now we need to differentiate yet again. Your instinct may be to expand out this bracket and multiply both by 1/3 pi, but a pro tip is that you don't actually have to do that, okay, because 1/3 pi is just a constant, so it really doesn't affect the actual algebra of the calculus. If you want to, what I'm going to do is I'm going to leave the 1/3 pi out the front, and I'm just going to differentiate the x's, because that's what really matters, okay? X is the variable. So if we do dv on dx, we've still got 1/3 pi, but now we have 4ax, and we have minus 3x squared. Okay, there is our derivative. Once again, we need to solve this equal to 0. Luckily, 1/3 pi is a constant, so we can just divide it away. And now we can notice that there's a common factor of x here, so we can do a cheeky little factorization. We're going to get two solutions from this. Either x is 0, which doesn't really make sense because then our cone doesn't really have any height, so that's the minimum value. We don't really care about that. We care about this one, 4a minus 3x equal to 0. If we solve that for x, it's a quick easy solve. We get that 3x is 4a, so x is 4a on 3. Okay, so that is a technically correct answer, which is the best kind of correct. But again, we need to show, giving reasons, why this maximizes using the second derivative if you want to get all 3 of the marks. Okay, so we will go back to our original function. We will derive this again. Once again, you can ignore the 1/3 pi and just leave it there and just work with the x's inside. So the second derivative is 1/3 pi out the front, 4ax turns into 4a, and the 2 comes down to make minus 6x. Okay, now once again, we're going to sub our value of x equals 4a on 3 into here, and hopefully we should get a positive or negative. Let's have a look. Okay, so subbing in, we get 6 times 4a on 3, which is 8a. So we get 1/3 of pi times 4a minus 8a, which is minus 4a. Okay. Now, what's important about that is that 1/3 pi is positive, a is positive because it's a length, but minus 4 is negative. So this whole thing must be negative. Okay. And if it's negative, in calculus, that's a frowny face, which means that it must be a maximum turning point. Okay, so the curve is concave down. Our stationary value is right here. It's a maximum value because it's a maximum turning point. And there's your reasons as to why this is a maximum. And there's your 3 marks. Okay, now we can have a look at our last example from the 2013 HSC. Again, another very difficult band 5-6 question. We have 2 straight roads meeting at R at a 60-degree angle. At time t equals 0, so initially, car A leaves R going this way, 80 kilometers per hour. Car B is 100 kilometers from R, so car B starts at this point here, and it's moving towards R at 50 k's per hour. Okay, the shortest distance between the 2 cars at any point is represented by R. Okay, now the first part is show that this function exists between R squared and t, which is pretty challenging, I'll be honest with you. And then the part B is find the minimum distance between the cars. Okay, so this is the clickbaity thumbnail that you're all here to see. It's a very difficult question, but there are a few tricks that make this a bit easier to manage, and hopefully this will make you more aware of them. Okay, so we're going to kick off with the first part, R squared equals 12,900, blah, 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 blah. Okay. So the first challenging thing about this question is that we obviously need to find R in terms of a length, but we don't have the lengths of, say for example in this triangle, we don't have BR and RA, all we have is speeds. Okay, so our first thing we're going to try and do is find expressions for this length here, which we'll call D1, which of course means that this length down here will be D3. No, I'm just kidding, I'm not a psychopath, that's D2. So the way we're going to get those is by realizing that distance and speed are of course related by time, aren't they? You learned in year 9 science, hopefully, that speed is distance over time, which means that distance is just speed multiplied by time. Okay, so you might think that our expressions for D1 and D2 now are going to be 50t, because that was the speed times time, and for D2, speed of 80 times time. But unfortunately, there's another level of difficulty to this one, because this length here is going to be 80t, because A starts from here. Okay. The second one, however, B, is starting from here. Okay, so if we did 50 times t, we would get this length here. Okay, so that one's actually wrong. We need to find this length here by using the fact that this is 50t. Okay, so the way we're going to get that is we're going to say, well, if this whole thing is 100 kilometers, this cross is 100 kilometers from R, and this length here is B's speed times time, which is your distance, this length here must be 100 take away 50t. Okay, so that's the first tricky part of this question. You might need to pause that and watch that a couple more times before that makes perfect sense. But now you've got that, the next part that's tricky is to figure out how you're going to form this function between r squared and t. Okay, now when I first saw r squared, I thought, oh, maybe we'll do a bit of Pythagoras, but unfortunately there's no right angle here, and we can't really assume that's a right angle without sort of being very dodgy. Okay, so instead we have a triangle, an angle, a side opposite. So what it's hinting at here is for us to use the cosine rule, okay, from trigonometry. So in this case, C and C are going to be R and 60, and A and B are going to be those lengths that we found from our speed equations. Okay, so we're going to sub that information into the cosine rule. So C squared is R squared, cos C is cos 60, which is of course a half, and we've got A squared and B squared and 2AB just here. Okay. Now we'll expand that all out, so be careful with this perfect square in red. Okay, 100 squared multiplied together and doubled, and then 50t squared. 80t squared is 6400t squared, and then like I said, cos 60 is a half, so a half times 80t is 40t. Okay, I'm just going to put that 40t at the front with the minus 2 to make it a minus 80, and now we'll just expand this bracket out by multiplying both terms inside by 80t. And we get this. Okay. Now that you've got that far, that's the hard work done. Now you just got to collect it all together, and we actually get the target of 12900t squared minus 1800t plus 10,000. Now, this one was definitely more difficult, so I wouldn't say quite easily done. I'd say not so quite easily done. I will give the marker a bit of credit. That was a challenge, but we did do it. Now at this point you might be horrified, but for me this is just the fun part, because now we can start applying some calculus. Okay, so part B is to find the minimum distance between the cars, and we've got the function of r squared that we just found. Now I'll be honest, the first time I did this question, I did it in the scenic route, I would say. I said to myself, well, I need to find r if I'm going to find the derivative of r. So I took the square root of both sides. Then I differentiated using the chain rule, and it was very, very messy. Okay, and upon further inspection, I realized there is actually a better way to handle this. Okay, we don't have to do the power of a half and the chain rule. We can actually approach this from a different angle. Okay, we can say to ourselves, well, if we're trying to find the value of t that maximizes r, that value of t should also maximize r squared. Okay, so if you want, you don't need to find r and differentiate. You can just differentiate r squared and just find that instead. It's going to be the same answer. Okay, so the value of t, which is going to minimize r, is also going to minimize r squared. Okay, so we're just going to take r squared, and we're going to do the derivative with respect to t, which as you can see is a much safer option. Okay, now once again we're trying to find a minimum point, so we need to solve equal to 0. This one's quite easy. We just do 1800 across, we divide by 25,800. And I'm sure you can all see the common factor of 300, or maybe 600 actually. 600 divide both by, and you get 30 on 43. Okay, so there is our time, which should hopefully minimize r squared, which was also going to minimize r. The only nice part about this question is that it didn't ask us to show that it was a minimum. So if you've got the right answer, you can assume that that's correct, okay? You can check it if you want, and if you don't want to find the second derivative, a nice way of checking is if it's a better option, you can use the first derivative. So if I wanted to, I could check both sides of 30 on 43, which is between 0 and 1. If I sub those into my derivative, I get negative and positive, which means that around this value of 30 on 43, I'm going from decreasing to flat to increasing. So it's going to look something like this. Okay, but anyway, this is just showing off. You don't have to do that. This is a minimum value, which means it's going to find the minimum value for R. Okay, so we sub t equals 30 on 43 into our original function, this part here. Don't forget the last trick that this is actually R squared. So to find your answer, when you put this through your calculator, you need to take the square root. And you should get roughly 61 kilometers. Pardon me, didn't put my units, but yeah, there's your correct answer. So this is a question that has lots of tricks to make it easier. And now hopefully that you've seen them, you might remember them for a future test that uses something like this. Okay. All right, so that's it for the questions. We'll just skip to the homework for today. So your homework is to give this video a like, so that hopefully it will go viral and I will obviously quit my job. If you could leave a comment, bit of feedback is appreciated. This took me quite some time to put together, surprisingly. So positive or negative feedback, greatly appreciated. Actually, we'll just stick to positive for today. Just positive feedback, thanks. And if you hit that subscribe button, if I ever get around to doing this again, in the event of a corona shutdown, you'll be the first one to know about it. So yeah, I just wanted to give this sort of a test run to see if I could make a video for the case of going online potentially in a few weeks. So yes, this was new for me. So if you made it this far, thanks very much for watching, and I'll see you later.